Okay. So today we're going to be talking about groups theory and like essentially like the basic ways of like classifying groups. And I guess before we can talk about the interesting things of like how we can like figure out what all groups of size, 7 are, we first need to define what is a group. So so what is a group? Well, a group is any any set of elements with a multiplication that has these following three properties. So the first property is it's closed. And what does that mean? Well, that means that if A is within the group and then B is within the group, that means that A is within the group. Okay. The second property is that it must be um, that it must have an identity. So what does this mean? Well, that means there is an element E within G such that AE equals EA equals A for all A. And is um the third is the inverse, which basically says that for every element A, there is a unique element A inverse such that A inverse A equals to the identity. I guess we can say there must exist a inverse. There must exist a unique inverse. Okay, so with these definitions out of the way, um, oh, I guess I forgot another property. Multiplication must be associative. So that means A times BC equals to AB times C. Okay, so with this out of the way, let's give some examples of groups. So for example, let's look at the real numbers. And in this case, the multiplication would actually be addition. So if we check, addition is in fact associative. A plus B plus C equals to A plus B plus C. In addition, 0 is that identity. It's obviously closed, right? And the inverse, A to the negative 1 equals to negative A. Okay, this is one example. I mean, we can also define like a multiplication, but for this, if we want our group to be multiplicative, then we have to restrict our elements to be bigger than 0. So in this case, we can have multiplicative group over real numbers, which again, if we have A, B, C equals to A, A, B, C, and then 1 is the identity, and then A inverse equals 1 over A. Okay, but these are two examples of infinite groups. What finite groups might exist? For example, if you've ever done any modular arithmetic, um, there is the group Z underscore N, which is addition, basically integers modulo N. And in this case, for example, you have um, you have like A plus B plus C equals to A plus B plus C. This is obviously associative. And again, we can check 0 is identity. And then negative A, or also N minus A is the inverse. Um, okay, so now that we have the definition of a group out of the way, we can start defining some other terms. For example, you might wonder, what are the quote unquote subgroups of a group? And a subgroup is essentially just a subset of the group, um, such that its multiplication is still like it still does the same thing, preserved. So, for example, if you have like Z20, like the multiples of 5 are a subgroup. And if you want to look at like other subgroups, you could also have the subgroup containing only 0. So these are some basic definitions of like groups, subgroups, this kind of thing. And we can derive some pretty interesting things. For example, if you have two groups A and B, then if we consider like the group consisting of elements A, B, where A is within A and B is within B, what we see is if we define our multiplication operation, A1, B1, A2, B2, to be equal to A1, A2, B1, B2. Essentially, we're just like mashing two entries together, right? And this actually defines another group, pretty obviously, where the identity is E for A and then E for B, and the inverse is A negative one and B negative one. So this group we would denote a, the product of A and B, which is a product group of A and B. So these are pretty nice. But how are we gonna like characterize the elements or size of the group? Well, there's a thing called the order, and the order of a group is essentially the size of the group. So for now, we're only going to deal with finite groups. And because we're dealing with finite groups, the order of infinite groups, those different cardinalities don't matter for what we're doing today. And so you can basically just think about this as the number of elements within your group. And a follow-up is like the order of a single element in a group. And the order of a single element might just be the minimum k such that so like if we want to find the order of G, or I guess order of G equals to minimum k such that G to the k equals to the identity. And the reason we define it this way is because now we can derive a subgroup for every single G, which is E G, G squared, dot, 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 all the way up to G to the K minus 1. And this generates a subgroup of order K, which is the order of the element. And this is kind of like why we define the order of a single element this way. Okay, so now let's give some more like abstract examples of like why might classifying groups like this actually matter. Suppose we had a square, and let's like color different corners of the square different colors. So we might say like let's say G is group of symmetries or rotations and reflections of this square. Well, how might we like define this group? Well, a group could rotate it by 90 degrees. So the red dot would go here, the blue dot would go here, the purple dot would go here, and the yellow dot would go here. That would be one element of this group. And another element of this group might be the red dot goes all the way to the purple dot goes all the way to the red dot. The blue dot goes all the way to the yellow dot, and the yellow dot goes all the way to the blue dot. So these groups of symmetries, we can actually figure out what the order of every element is. So for example, a 90-degree rotation. Well, if we rotate it once, it's obviously not the same element, right? But if we rotate it twice, it's also not the same element. But if we rotate it three times, it's also not the same element. But now when we rotate it four times, it's essentially a 360-degree rotation, which gives you essentially the identity element. So the order is four. Now consider like a reflection. So if we reflect across the x-axis, the yellow dot goes to the blue dot goes to the yellow dot. And we can see that the order of this reflection, reflect across x, the order of this reflection is order 2. And if we want to figure out the order of this group, well, through some inspection, we can draw all the reflection lines. So you have one reflection here, you have one reflection here, you have one reflection here, one reflection here, and obviously you have four rotations. And so you have 8, like the group has order 8. So this shows that we can use group theory to essentially characterize how things are moved around, like how a set is being mapped to itself, um, rather than just on how a group acts on itself. And so this like kind of study about symmetries, you can study more about it when you talk about group actions and stuff like that, but I won't go too much into detail there. I guess for us to classify groups, what I want to define now is an isomorphism. And essentially, what this means is in this context, we're going to say that if there is an isomorphism between two groups, like let's consider those groups essentially the same. And what do I mean by that? Well, there is a mapping phi such that, I guess, from group A to group B, such that it preserves multiplication. So what do I mean by this? Well, if phi of A, B, the way you would figure this out is you would find phi of A and then phi of B, and then you basically would need this to be true. Um, and phi must be a bijection. Okay, so let's give an example. So for example, Z4 Z2, and let me want to find an isomorphism from Z4 to Z4. So one way you could have this, you could just map 0 to 0, 1 to 1, 2 to 2, 3 to 3. This would be one isomorphism. But you might also realize that 0 maps to 0, 1 maps to 3, 2 maps to 2, and 3 maps to 1 is also an isomorphism. Because let's say you had A and B here, right? Then phi of AB in this case, just to demonstrate for 1 and 3, phi of 3 is 1, right? And in this case, if we do phi of A times phi of B, this also maps to 1. So this is also an isomorphism. I guess more generally, if we consider our square group example, we might say like, okay, let's say I want to find an isomorphism from this mapping to, let's say, a permutation on 1, 2, 3, 4. Well, not wait, this won't be isomorphic to the general permutation group. But if we restrict it to a certain set of permutations, um, then what we see is like, for example, let's say 1 is the red dot, um, 2 is the blue dot, purple is this dot, and then um yellow is this dot. Or yellow is 4. And suddenly what we notice is that every group element over here, for example, a rotation by 90 degrees, essentially what it's doing is it maps the red dot to the blue dot. So 1 goes to 2. And then, or the permutation would be 2, and then blue goes to purple. So this would be 3. Wait, wait, no, this would be 1, 2, 3, 4, actually. Yes. So this permutation would be a 90-degree reflection. And then, for example, if we like find a different like or 90-degree rotation. And if we use another example, for example, if we reflect across the x-axis, that would be the reflection 1, 3, 4, 2. And this would be reflection x reflection. So we found one isomorphism from this like this rotation group to like this set of permutations, but there are actually other isomorphisms. For example, if we just scrambled the order of these yellows, reds, blues, and purples, we would get different isomorphisms. But for now, you can just think of it as like an isomorphism just tells you these two groups are functionally doing the same thing. Like, for example, if I'm doing something on this permutation, it's functionally the same as if I'm rotating or reflecting this square, um, which is, um, I guess, mathematically how we're going to classify these different groups. Um, okay, so now let's go through a couple theorems. So this is by Lagrange. And what this theorem tells us is essentially that any subgroup or the order or size, if yeah, order of any subgroup must divide the order of our overall group. Um, and the way we might prove this is as follows. So suppose our subgroup is H and our overall group is G. Then consider an element G within G, but not within H. So you consider the elements of H, like uh, E, H, blah, blah, blah. And what you notice is HG, like for example, EG must be outside of H. HG must also be outside of H. Because if HG was within H, let's say it was H2, then G equals to H inverse if we multiply H inverse on both sides times H2, which is within H because the group is closed. So that means that HG is also not within H. And that means that every right product, like H2G, H3G, dot, dot, dot. These are all not within H. And so now what we notice is, let's say we add this to our set, and now we say, what if we find an element that isn't included in the set of these or the set of these? Then we apply the same argument, right? So let's say there's G2. Then EG2 cannot be within one of these two sets. Because if it were, like, let's say it equals to like sum H2 times G, then we would see that, like, let's say this is H1, that then we see that G2 equals to H negative 1, 1, H2 G, which is which must be within this set. So that contradicts what we originally did. So every time here, when we find a new element G, we're increasing the size of this set by H. And eventually, this will have to be exactly our overall group, which means that the order of G, or which means the order of H must divide the order of G. Um, yeah. Okay. So a nice corollary of this is that all all orders of elements in a group must divide the group's order. So for example, like if you had, like, for example, Z8, then that means the orders of all the elements are 1, 2, 4, or 8, and it cannot be anything else. And the reason for this is because remember earlier when we generated for a single element G, we generated a group E, G, G squared, dot, 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 to G to the K minus 1. Well, this, remember, this is a subgroup of order K. So that means that by this theorem, that means that K divides the order of G. But since K is our original element order, that means the order of all the elements within G must divide G. Okay, so now I'll present the following theorems, the Sylow theorems. The proofs aren't that difficult per se, but um, they're also they're pretty mathematically dense and they require a few more definitions, so I won't go over them too much. But the statements for these theorems should actually be relatively intuitive. And theorem one states that for any n, which let's prime factorize it into p1 to the e1, p2 to the e2, dot, 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 pn to the en. There exists a subgroup of order pi to the ei for all I. And this is not completely obvious, but it's also like pretty trivial if you think about, like, if you think about any group of order n, then it makes sense that there should exist this kind of group, although the proof is a little bit more involved. And then theorem two says that all subgroups of order pi to the ei must must be conjugate. What does this mean? Well, that means that suppose you had two subgroups A and B, which were subgroups of order pi to the ei. Then um, B must be equal to G A G to the negative one for some G. Um, and this is also not totally obvious to prove, but if you think about how a group's structure works, it is not too hard to convince yourself that this fact is in fact true. And then theorem three states that the number of subgroups of order pi to the ei must be 1 mod pi and divide n over pi to the ei. And this one is a little less obvious, but it is also similarly easy to convince yourself that it is true. Okay, so now we have this out of the way. Let's begin trying to classify some groups. So let's start with an easy case. What if we want to find all groups of order, which is P, and P is a prime? Well, remember from before that all elements must have order 1 or P. But clearly, if an element has order 1, this implies it's the identity, right? Because remember, our definition of order is the minimum power you have to take this element to such that it's it becomes the identity. So if we're taking it to the first power, that means it itself must be the identity. So that means that we must have every other element have order P. But if we have a single other element with order P, then we can actually generate the whole group because remember, E P P squared dot 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 P to the K minus 1 is like a subgroup of G, right? But this has P elements. Or no, say G. But this has P elements, right? So that means that this must actually be G. Um, and so that means that the only groups of prime order are um like these, which is like essentially isomorphic to ZP. Okay. Um, let's try to formalize this like idea of generating a group because that might be helpful for non-prime orders. Um, so suppose we wanted to generate suppose we wanted to generate a group of order from two elements, A and B. And let's say we wanted A to have order like 7, right? And we wanted B to have order 3. What would we need to do? Well, we would essentially need to be able to define any sequence of multiplications A, B, B dot dot dot, A, B dot dot dot. Um, and this is sufficient because if we consider our like if we consider all of our elements A to the K1, B to the K2, where K1 is from 0 to 6, and then K2 is from 0 to 2, then uh what we see is that like any multiplication with a bunch of different elements within this group can be turned into a multiplication of a bunch of A's and a bunch of B's. So, in fact, if we're able to figure out what BA is as like A to the something times B, then we can actually move all of the elements, like all the B's that are before A's, after them. And so we'll eventually be result like, for example, if we had B, B, A, we would be able to move this B beyond this A. So like, let's say, for example, this is A squared. Then we would be able to move this B beyond the A. So this is equal to B A squared B. Okay. And now we would be able to move this B. So this is B A to the 4B. And then we move this B. So then this would be A squared B A cubed B. And then we can repeat this process until we get something that is A to the 8B squared. And once we have all the A's before all the B's, now since we know that A to the 7 equals to the identity and B to the 7 is the identity, or B to the 3 is the identity. Now what we can do is we can reduce this into AB squared, which is like one of our canonical elements of the group. Thus, all we need to do is be able to define this action of this. And if we reorganize this means we essentially need to define exactly what this value is, which is commonly called conjugation. And this is part of the reason why conjugation is considered such an important operation that is so often studied in group theory. Because another nice property of conjugation is that the conjugate must have the same order as the original element. For example, if we take A has order 7, then B to the negative 1 to the 7 equals to B to the negative 1, and then B to the negative 1, and then dot, 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 and then B to the negative 1. And you'll notice here that these B to the negative 1 and B, these cancel. And then the B to the negative 1 and the B on the next one, they cancel. And so what you end up with is BA to the 7, B to the negative 1, which is just equal to the identity. So conjugation preserves the order of the element. And that's also part of the reason this is so important. So if we want to generate a group with order 7 or with order like 21 from two different elements, we need to define the order of A, the order of B, and how A and B conjugate with each other. So B to the negative 1. And once we define these three things, we can generate a group from A and B that is exactly order 21. So what we would say is we would say that it's generated with A to the 7 equals B to the 3 equals 1, and the definition of the conjugation, like A squared, for example. And what you'll notice is conjugation also forces your any isomorphism to preserve this conjugation. And so that means conjugation must define a unique thing that isn't the same to any other generation by conjugation. And what we've shown before is that this conjugation generates a unique group. So every group generated by this conjugation must be of that form. So this is how we're going to be generating our groups. So now let's consider like something of the form P times Q, like for example, 21. What you might originally try is like, okay, so you have Z PQ as one possible group, right? And now you might say, okay, ZP cross ZQ is another group. However, this is actually isomorphic to ZP times ZQ. And the reason this is isomorphic to ZP or ZP times Q is because consider like uh consider in any element A, B. If like by Chinese remainder theorem, there exists a unique element X such that X is congruent to A mod P and X is congruent to B mod Q. Well, what does this tell us? Well, this defines an exact isomorphism, right? The unique element X under in, I guess, dp times q. This defines exactly an isomorphism. So for example, for AB, we would map it to this X such that X is A mod P and B mod Q. And notice that when we add the addition, like it stays the same. Like for example, x1 plus x2 equals to x1 plus like x1 plus x2, which if we wrote it out as a1 times b1 plus a2 times b2, notice that when we add x1 and x2, a1 and a2 add. When we add x with b1 and b2, like well, it adds on the second term as well. And so these two are actually isomorphic. So um, we don't actually just have two trivial groups. And in fact, for certain combinations of P and Q, ZPQ is actually the only possible group. So when might we have more groups? Well, let's try to generate these groups. Let's say we want to find an element A with order 7. Well, we actually know by Sylow's third theorem, we know that we know that the number of groups of order or subgroups of order P is uh, is 1 mod P and 0 mod or not 0 divides n over P, which in this case is P times Q over P, which is Q. So if it's a divisor of Q, it must either be 1 mod Q or it must either be 1 or Q. So let's say suppose P is greater than Q. Otherwise, we could just reverse P and Q and the same logic holds. Then Q cannot possibly be 1 mod P anymore. So that means that there can only be one subgroup. What does this tell us? Well, if there's only one subgroup, that means that there are only P minus 1 elements of order P. And otherwise, you could just use a different element to generate a different subgroup that is also of order P that would contradict what we found. So because there are only P minus one elements of order P, what we can do now is we know that, like, let's say we conjugate an element G has order P, or I guess A is better. Then let's say we conjugate it by any element G within our group. Well, remember conjugation preserves order, right? So conjugation must preserve order. And so GA, G to the negative one must also be within this sub P group. So that means that GA, G to the negative one must equal to A to the K for some power of K for this specific A. And what you'll realize as well is GA squared, G to the negative one, must be equal to GA, G to the negative one times GA, G to the negative one, which is equal to AK times AK, which is A to the 2K. So A to the, okay, so if we conjugate GA to the J times G minus one, then this must equal to A to the JK. This is pretty promising. So what we can see now is that our conjugation actually defines the conjugation for everything else. And supposing we knew the order of G, if we knew the order of G, uh, like equals to K2, then we know that G to the K2, A to the J, or A G to the negative K2 equals to obviously equals to A, right? And we can see that this is G to the K2 minus 1 times GA G to the negative 1, G to the negative K2 plus 1. Here we see that this is A to the K. And so what we see is this eventually equals to A to the K times K2, which also must equal to A. So what we found is that K times K2 must be like A to the K times K2 must be equal to A. And and so what this means is that um you must have A times K2 minus 1 equals to 1. So that means that K2 times K this must be congruent to wait, oh wait, no. Okay. So now that we know this, let's say we considered the group consisting of A, or not necessarily a group, but the set consisting of A and then A to the K and then, oh wait, no, yeah, this is K to the K2, A to the K squared, and then dot dot dot. This also must, like, you must have like, so okay, suppose we knew the order of G, which, because we know our group is order P times Q, we also know there must exist an element of order Q. So let's say we conjugated by that element of order Q. Then that means we know that A to the K to the Q equals to A. And so K to the Q is congruent to 1 mod um mod P minus 1. And so that means that we know that Q must divide P minus 1. So if Q does not divide P minus 1, then we are done. We know that ZP times Q is the only possible group. Otherwise, let's say, like, for example, for 21, we still need to generate what possible other groups might exist. So in this case, let's consider the possible values of K. So in this case, P equals 7, Q equals 3. So when we do the math, we see that um, G to the negative 1 equals to A to the K. So let's say K equals to something that's not 1. Because if K equals to 1, then we get back. So K equals 1 gets back ZPQ, which we don't want. We already know that it's a group, basically. So let's try K equals 2. So if K equals 2, that means that A must go to A squared, which must go to A to the 4, which must go to A. And similarly, uh, A must go to, um, or A cubed must go to A to the 6, must go to A to the 5, must go to A cubed. So that means that this generates a group where we have A to the 7 equals to G to the 3 equals to 1. And we know the conjugation where G to the negative 1 equals to A squared. So now we've generated another group. Let's try K equals 3. So for K equals 3, we have A goes to A cubed, goes to A to the 9, goes to A to the 27, which is A to the 6. Uh, but this is not good, right? Because uh, we need to apply this 3 times and get back to A. So K equals 3 doesn't work. K equals 4, A goes to A squared, goes to A to the 4, goes to A, and then A goes to A cubed. Wait, no. A cubed goes to A to the 5th, goes to A to the 6th, goes to A cubed. So this might generate another group. So A7 equals to G cubed equals to 1. G to the negative 1 equals A cubed. However, the problem with this is that this actually doesn't generate another group. And the reason this doesn't generate another group is because we can find an isomorphism from this group over to this group, where you might notice, oh wait, this should go 4 to 2. You might notice that in this case, things are going in the forward direction, and in this case, things are going in the backwards direction. So if we just define our isomorphism to go essentially the other way, then we've found an isomorphism between these two groups. And the isomorphism is a little bit messy to write out, but essentially you're mapping the map from here to here to be a different, like a different element, and then the mapping from here to here is similarly a different element. And this actually generates an isomorphism between these two groups. And so that means K equals 4 hasn't generated another group. We can check K equals 5 and K equals 6, but they suffer similarly to K equals 3 and don't generate another group. And so at the end, we've classified all groups of size 21, which are Z21. And this kind of interesting and weird semi-direct product of this. So these are all the groups of size 21. And we can do the same thing for, like, for example, 6, for example, not, yeah, 6, and then 10, We can do a similar thing for like 55. Basically, anything where Q divides P minus 1, we can generate a second group um, that is defined this way, such that um, its conjugation just works. And we can show actually that those are the only two groups for, I think, all of them. Uh, yeah, I think these are the only two groups of size p times q, where q divides p minus 1. Okay, so let's try something even harder. Let's try 4. Well, 4 isn't too bad because in this case, we can just generate what every element must go to. So we must have an identity, so that's already there. Now let's suppose we have an element A. A must either have order 2 or 4. So okay, so suppose A has order 4, then this must generate the whole group. Otherwise, if A has order 2, then A cannot generate the whole group. So now we need another B. So let's say this has order 2. So if B has order 2, then our possible products are A, B, and AB, and this generates another group. But if B is order 4, so let's say B is order 4, then B must generate another group. B squared, B cubed. And now this is too many elements. So that means we know that A equals B squared. And so we can discard this case. So for 4, there are these two groups. This one isomorphic to Z4, and this one isomorphic to Z2 cross Z2. And notice here, Chinese remainder theorem doesn't apply. And the reason it doesn't apply here is because these two, even though they're both prime, they're not co-prime with each other. And so Chinese remainder theorem doesn't work. So now with 4 out of the way, let's actually try a slightly more complicated case of, for example, 20. What groups of size 20 can exist? Well, from Sylow's third theorem, we know that number of order 5 groups or subgroups is 1 mod 5 and divides 4. So this means that it must be 1, 2, or 4. Obviously, 2 and 4 do not work, so it must be 1. And again, that means we must have 4 elements of order 5. And we can canonically order them A squared, A cubed, A to the 4. Okay, so now once we have this, we can do some casework. We know there must be a subgroup of order 4. And so that means there's two cases. We either exist some order 4 elements, or there exist no order 4 elements. So, okay, let's do the case where exists order 4 elements. Then let's say that element is B. So that means B to the 4 equals 1. And we also already know that A to the 5 equals to 1. Now, what we want to do is we want to figure out what B to the negative 1 is. Because this is all that we need to be able to generate the entire group. So B to the negative 1, again, it must map to an order 5 element. And since we know there's only one group of order, subgroup of order 5, it must map to A squared, A cubed, or A to the 4. So let's say it maps to A to the K. So again, um, we do the math where we see that b to the 4a, b to the negative 4 equals to a to the k to the 4 equals to, um, and this equals to a. So that means k to the 4 is congruent to uh 1 mod p, or not 1 mod 5. So that means that basically k can be anything. Okay, so let's try k equals 1. K equals 1, we get b to the negative 1 equals to a. So that means ab equals ba, which means our multiplication must be commutative. So that means that this essentially becomes Z4 cross Z5, which again, by Chinese remainder theorem, um, we get Z20. So now for k equals 2, we have b to the negative 1 equals to a squared. So um, this generates a new group defined by a to the 5 equals b to the 4 equals to 1, or no, and b to the negative 1 equals to a squared. K equals 3, you have b to the negative 1 equals a cubed, and then a to the 5 equals b4 equals 1, so that b to the negative 1 equals a cubed. So now, are a squared and a to the a cubed, are they in isomorphism? And turns out the answer to this question is yes. And the reason is because, so imagine here you take a, you go to a squared, you go to a to the 4, and you go to a cubed, you go back down to a. So that means that you must have an element b to the negative 1, which actually maps from a to a cubed and back to a to the 4 and back to a squared and back to a. So if your isomorphism maps a to a and b to b inverse, then you can have an isomorphism between k equals 2 and k equals 3. So this case actually is isomorphic to k equals 2. So now for k equals 4, b to the negative 1 equals to a to the 4. So a to the 5 equals b4 equals to 1, b to the negative 1 equals a to the 4. Is this now isomorphic to the original group? And it turns out it's no. And the reason for this is because we map a to the 4 back to a, and a squared to a cubed back to a squared. And this is fundamentally different in its overall structure than our original group. So we've actually, in this case, we've generated 3 different subgroups. And now, if there's no order 4 element, we have, um, so we must have 2 elements this time, b squared equals 1 and c squared equals 1, such that b and c are different. And so now we have a bunch of cases to go over. So in this case, to generate a group of 3 elements, we need to be able to reverse our product in such a way that it goes a to the k1, b to the k2, c to the k3. So we need to be able to define a way to get all the a's in front of all the c's. And then we also need to define a way to get all the b's in front of all the c's. And now once we do that, we know all the c's are at the end. And now we need to define a way to get from all the a's, or get from get all of the A's in front of all of the B's. So essentially, we need to define conjugation. We need to find BA, B inverse. We need to define CA, C inverse. And we also need to define BC, B inverse. Well, this actually, the fact that we have four here is very convenient because in this case, these must determine their own group where you have b squared equals 1, c squared equals 1, and bc, b to the negative 1 equals 1. And in this case, this is like very easy to deal with because this must be a group of order 4 or equals something. And it turns out that these must actually be abelian. So BC, b to the negative 1 must actually be C, which is pretty nice. So um, we've essentially reduced our cases to BA, b to the negative 1 and CA, c to the negative 1. So um, we also know that like when we conjugate b squared a b to the negative 2 equals to BA, b to the negative 2, negative 1, b times negative 1. So essentially we're conjugating this, and when we conjugate this, we get BA to the k, b to the negative 1. So that means a k squared must equal to a. So that means k must be 1 or 4. So we can essentially just brute force on all possible combinations of 1, 4 for BA, b to the negative 1, and CA, c to the negative 1. And it turns out one of those cases is completely symmetric. For example, if one of them maps it to 1 and the other one maps it to 4, it's the same as if the other one mapped it to 4 and the first one mapped it to 1. And so so our first case is both map to A. And in this case, it's quite obvious that since BA, b to the negative 1 equals A, and CA, c to the negative 1 equals A, we also know that B, C, b to the negative 1 equals C. So from this, we know that multiplication is commutative. And because multiplication is commutative, we know that this must be isomorphic to Z2 cross Z2 cross Z5, which if you also want to write it in a different way, this is Z2 cross Z10. Okay. Now, what if one of them maps to A? Then that means that BA, b to the negative 1, let's say this maps to A to the 4, and um, CA, c to the negative 1 maps to A. So now what we see is that this group, this part, must define essentially a product group where it's like the thing defined by the C is Z2, and then we're essentially crossing it by A to the 5 equals B squared equals 1, and BA, b to the negative 1 equals to 1. Or not 1, A to the 4. And the reason for this is because C is commutative with everything else. And so that means that uh, the operation of C must be the direct product group with the rest of the other group. Um, and that allows us to do this. So is this group isomorphic to anything we had above? Well, if there is an order 4 element, then obviously it's not isomorphic to it. And if there is no order 4 element, since we know that b to the negative one is is not a, that means that we know this is not actually an isomorphism to our commutative group. So this must define a new group. Um, and what this group does essentially is you have an element B and it maps A to the 4 back to A, and then A squared to A cubed to A squared. And now our third case, where both B and C don't commute, uh, don't commute. Now we see that B to the negative 1 equals to A to the 4, and C to the negative 1 equals to A to the 4. So this means that BC A to the negative 1 equals to B times C to the negative 1, B to the negative 1. And the reason for this is like note that BC to the negative 1 um, times BC equals to the identity. So if we wanted to figure out what the identity, or what this inverse actually is, we would first right multiply by C to the negative 1 and then cancel. Uh, and then we right multiply by B to the negative 1. So you'll notice that in this case, inversion actually inverts the order in which you invert things. And that's extremely convenient here because now C to the negative 1, we know this is equal to A to the 4. And we know that this is equal to A to the 16, which is equal to A. Uh-oh. Well, we found another thing. Clearly, this has order 2, and this maps A to A. So this is actually the same case as before. So in this way, we found all 5 different groups of order 20. So we have Z20, we have um, we have the product group of, or semi-direct product of this, where your multiplication is defined by A squared. And then you have another one similarly, which is A to the 5 equals A to the 4 equals 1, B negative 1A, B equals to A to the 4. And your last two groups are Z2 cross Z10 and A to the 5 equals, okay, Z2 cross A to the 5 equals B squared equals 1, and B to the negative 1 equals A to the 4. So um, we've essentially classified the types of groups of order P times Q, and now of order like 4 times 5, which actually you can generalize this exact approach to 4 times 7, 4 times 11, 4 times 13. And I actually encourage you to actually do the math and try out these cases. Um, and I think it'll be pretty rewarding. Um, yeah, for other types of numbers, I also encourage you to try. Like, for example, for generally p squared, what must be the groups? Um, and for p cubed, what must it be? For general p squared q, what must it be? And so on and so forth. Um, yeah, I encourage you guys to take what you've learned and try to apply it to these slightly more complicated examples. Um, but yeah, this is kind of like the end of what I was prepared to talk about. If you have any questions, you can feel free to ask. Okay. If there are no more questions, then I think we can call it a day. Thank you so much for listening, and I hope got something from this talk and can apply it to try to solve some of the examples that I gave. Thank you so much.